4 centuries ago, Galileo Galilei declared,
"The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. Without these, one is wandering about in a dark labyrinth."
Mathematics is the light that leads scientists out of the dark labyrinth of misunderstanding. Sure, telescopes and microscopes, observations and experiments have a role to play, but I believe mathematics is the driving force behind modern science. We celebrate the scientific genius of Albert Einstein, but what about the pioneering mathematicians on whose shoulders he undoubtedly stood? Particle physicists today are deeply indebted to a mathematician who was killed in a duel just after the French Revolution. And the mathematics of a Napoleonic soldier is the reason that you can hear me now. I should probably declare an interest at this point. I'm a mathematician, and in my view, mathematics is the language of the universe. Mathematics is the queen of science.
A brief history of mathematics with Marcus du Sautoy.
In Europe, in the late 17th century, where this brief history of mathematics begins, 2 exceptional mathematicians, one pure, Gottfried Leibniz, and the other more applied, Isaac Newton, were working on the same problem at the same time. Sir Isaac Newton, that great hero of British science, was described in an early school report as being
inattentive and idle.
Still, he went on to study at Cambridge, and in his early 20s started work on a new mathematics, the mathematics of moving things, or calculus. He described this new mathematics to friends, but didn't publish any account of how he did it, a decision that was to have ugly consequences, for at the same time as Newton was busy with his calculus, the young German scholar Gottfried Leibniz came up with a different version of the same thing. Now, whatever you thought of calculus at school, I'm here to try and make it clear. Bottom line, the calculus is a way of describing things that change. Take the famous apple that legend has it fell from the tree onto the young Newton's head and inspired his theory of gravity. At any particular point in time, how fast is the apple falling? The speed of the apple I just dropped is constantly increasing as gravity pulls it to the ground. So, how can you calculate what the speed is at any given instant of time? For example, after 1 second, how fast is the apple falling? What about after 2 seconds? Speed is the distance travelled divided by the time elapsed. So, I could record the distance the apple drops in the next second, and that will give me an average speed over that period. But I want the precise speed at a precise moment, like now. Well, I could record the distance travelled over a shorter period of time, say half a second or a quarter of a second. The smaller the interval of time, the more accurate my calculation of its speed. But, ultimately, to work out the precise speed at a precise moment of time, I need to take an interval of time that is infinitesimally small. But then, I'm faced with calculating 0 divided by 0. The calculus makes sense of this seemingly impossible calculation. It tells you what the speed of something is tending towards as you make the time interval smaller and smaller. Calculus is the mathematics of things on the move. In mid-17th century Europe, this new mathematics of moving things was something that both Newton in England and Leibniz in Germany understood. In July 1676, Leibniz, who was travelling round Europe, received a letter from Newton. Newton had sent the letter to Henry Oldenburg, the first secretary of the Royal Society, who'd sent it on to Leibniz. In it, Newton described his version of the calculus. But he didn't share any of the crucial details about how it worked.
Sample complete. Ready to continue?